Hello, we're Team 6, sponsored by Unilever, and I'm Jillian Murray.
I'm Andrew Colville.
I'm Christina Coakley.
And I'm Daniel Fernandez. This is our project on the end-to-end model integration for the development of a standardized design method.
Unilever's current method of product development lacks a generalized structured data workflow for product and process design that aligns with its digital-facing strategy and sustainable living plan. Due to this, the company is seeking to maximize its learnings surrounding process development while minimizing required resources. The objective of this project was to use a case study on Dove body wash to see if the designed method could create several predictive and iterative models. From these models, Unilever will be better equipped to identify key risks along the product development pathway. Dove body wash is an established Unilever product. Therefore, the company understands the impact of surfactant structures and manufacturing input parameters on the rheology of this non-Newtonian fluid. This prior knowledge was paired with several mathematical models to develop and validate the newly designed method. The Herschel-Buckley equation served to approximate nonlinear fluid behavior, while the Hagen-Poiseuille equation correlated product viscosity to manufacturing pressure gradients. This knowledge served as the foundation of the experimental design.
This figure outlines the method our team developed to standardize Unilever's product development. The first phase is the formulation cycle, which consists of developing the formula, identifying key formulation variables, and completing a robustness DOE with an internally created robustness assistant. Using JUMP to analyze the experimental data and gain insights about the formulation creates the foundation for the next phase, the process cycle. This consists of developing the manufacturing process, identifying key process variables, and completing the process robustness DOE using JUMP and the digital manufacturing platform, an internal tool developed to collect process data. The final cycle consists of building models supported by data from the formulation and process cycles to run simulations. By completing rheological assessments using a rheometer and using digital tools like JUMP, DMP, Power BI, and LIMS, 3 deliverables can be made: a right first time prediction, a filling model, and a viscosity prediction model.
The formulation cycle was used to find the main ingredient drivers within the product formulation by varying initial ingredient weight percentages. Through running the DOE created by the Robustness Assistant tool, data was collected and analyzed to determine that lauric acid was the main driver of both pH and viscosity, validating that the methodology can identify ingredient risk within the formulation. The process cycle was used to establish if the manufacturing process affects the robustness of the formulation. Data collection in the pilot plant enabled the simulation of batches and their viscosity, shown by the grade distribution on the graph on the right. The pilot plant simulation has a much smaller distribution than the lab simulation data, implying that the process increases formulation robustness. Furthermore, the discrepancy in viscosity values between pilot simulation and factory data can be explained by an interaction between the process and the formulation. Therefore, right first time confidence is contingent on further experimentation to identify this exact interaction. Using the body wash produced in the pilot plant, a rheological sweep was performed on each batch from a shear rate of 0.1 inverse seconds to 1,000 inverse seconds. Multiple insights can be obtained from this sweep curve, including single-point viscosity measurements at a given shear rate, as well as the Herschel-Buckley parameters by fitting the data to a line. The single-point viscosity measurements were correlated to at-line delta pressure readings to establish a model, which can be seen on screen. The model is fairly accurate in its ability to predict product viscosity from at-line delta P readings mid-run, thus allowing for the specification of the final product to shift from a single-point viscosity measurement directly to the live pressure reading.
The purpose of our developed filling model is to predict the flow pattern for each bottle geometry based on rheological inputs. For each batch of body wash, a rheological sweep was run to find the Herschel-Buckley parameters per batch. These experimental values were also simulated to create the featured contour plots. As seen in these plots, the successful operating window shifts as a function of bottle geometry. For example, the green sections of the contour plots for the circular bottle show where the filling pattern was successfully predicted. Through increasing fill accuracy, the amount of waste produced in factories and amount of required headspace will decrease, saving Unilever valuable time, money, and resources.
Each model helped to unlock new insights about the product development cycle. The RFT model successfully identified formulation and process risks throughout product development. The filling model proved that different bottle geometries do impact the fill success. The viscosity model helped to develop delta P specifications for the factory with minimal experimentation. There will be significant financial advantages through waste and raw material reduction along with an overall capacity increase. The project aligns with Unilever's sustainable living plan by greatly reducing the product produced per development cycle. One next step for the project is further confirming the robustness of the proposed methods by continuing case studies. All in all, the major takeaway is that the completion of this case study shows that these methods can maximize learning while minimizing resource investment.